Let us start with the lecture Introduction to Statistical Learning Theory. The main problem that is studied in statistical learning theory is known as statistical inference. This can be roughly defined as follows. Basically, we have a set of observations. These observations can be measurements of physical processes such as atmospheric phenomena like rainfall, soil moisture, temperature, and so on. Or it can be just social, and or it can be data from, for example, social media. So the background is that we have an unknown functional dependency or unknown functional structure that actually generates this data. For example, in physical measurements, if you are trying to measure rainfall from space, you basically use either infrared sensors or microwave sensors based on satellites. These sensors do not measure the rainfall directly. They usually measure the radiation temperature either in microwave or in infrared spectrum. So the problem is, how do we infer the actual hidden parameter, that is the rainfall, from these indirect measurements? So basically the problem is, how do we infer physical or hidden variables or hidden processes from indirect measurements? In the case of social media data, the functionals are not very well understood. That is, in the case of physical processes, the functional dependencies are usually very well understood and defined. For example, in the radiation temperatures that are measured from rainfall data have a very sophisticated radiative transfer models, which are very well known. And these models are usually inversed for inferring the rainfall information. But in the case of data like, say, social media, data from Facebook or another social media, it is far more difficult to understand the functional structure behind the process of this data, the process that generates this data. So the problem is, how do we actually understand this functional structure, which is the central goal of statistical inference. So let us look at some history of statistical inference. In the beginning of 20th century, there were many methods that were developed to solve this problem of statistical inference, especially from the point of view of a parametric inference. Basically, for example, Fisher used maximum likelihood method to solve attempted to solve the main problems of statistical inference, which are basically classification, regression, and density estimation. So he used a parametric model to define the respective problems, and the main goal of this research was to infer these parameters from data. Later, some work on convergence and asymptotic properties of this convergence. For example, Glivenko and Cantelli proved that empirical distributions, that is the parametric structures defined to solve the inference problems, actually or usually converge to the true distribution given sufficient data. And Kolmogorov later also determined the rate of convergence to be exponential. That is, as the number of data or amount of data increases, the distribution or the parametric structure actually converges to the true structure at an exponential pace. Now let us look at the two main approaches to statistical inference. The first one is known as parametric approach, which is based on simple models, that is simple linear models, for example, and usually addresses real-world problems. And the next approach or next problem, or the more general problem in statistical inference, is the problem of general statistical inference. So the goal of this type of approach is to study very general class of problems, and there is no limit on the structure. The functional dependencies need not have any parameters or predefined parametric structures. So let us look at what is this parametric method. What are the parametric methods used for solving the statistical inference problem? A general setup of parametric method is that a researcher knows the science behind the processes that lead to the randomness in data. For example, let us consider a radar parameter estimation problem. Basically, you have a radar and you have a target, and you are trying to measure some parameters of the target, like its range and what is the angle, that is direction of arrival of the target towards the radar. These all can be done by impinging radio waves from the radar, basically by radiating or basically by radiating microwave or radio waves, electromagnetic radiation towards the target and measuring the reflected energy. So the goal is to estimate some parameters regarding the target. So in a problem like this, the researchers usually understand the physical process underlying these observations. That is, in this case, the reflections from the or scattering energy from the target. But there is still some interfering signals coming from other unknown clutter, or there could be some, and there is also usually noise in the receiver. So these are random components of the observations. And then then the researcher actually develops a parametric structure for the observations, which basically relate to the true or the underlying physical processes, and also some of the parameters correspond to the noise components. And the classical approach is to use a maximum likelihood approach to solve this problem. So as I mentioned, this is a linear model which is also typically used in radar problems to relate the observations, that is the reflected energy or the received energy, to the actual target parameters, and W corresponds to the random noise in the receiver. So basically this Y corresponds to observations, X corresponding to hidden variables, and A is the linear weight that relates to the two, and W is of course usually considered to be a Gaussian random noise. So the goal is to estimate X or the structure of X from these observations. And now coming to the next approach, that is the general statistical inference. Characteristics of the problem are that the prior information is not usually available on how the random components of the data emerge, or the random components of the model emerge, or what are basically the probabilistic models of the random component. We do not really usually know this structure. And sometimes even the data model, like the linear model in the previous case, is also not known. So the goal of the problem is obviously to infer these inherent structures and also the statistics of the random components. So the challenges with this type of general statistical inference is that we have an empirical data set that is available, which can be, as I said, either from physical processes or from non-physical processes, and we have a set of possible functions. The goal is again to find a best approximation that defines the data, or that describes the patterns in the data. And major problem is how do we find this approximation using a set of examples. The goal is to find the functional approximation by using training data in a supervised learning setting. So let's look at the pillars of a parametric approach. So before 1970s and 1960s, that is before the widespread application of computers for solving real-world problems, the parametric methods were widely applied for statistical inference. This is true for at least 3 decades before 1970s. So why is the parametric method or the parametric approach the most widely used method in statistical inference? These are the 3 pillars. They are the 3 foundational components of the philosophy behind parametric approaches. The first one is, of course, the functional dependency. That is, the researcher or the statistician has a good understanding of the underlying functionality of the observations. That is, what produces the observation, how the observations are produced from hidden variables or the underlying physical processes. And also he has a good understanding of the stochastic components of the models, that is, the probabilistic models. And the assumption is that this functional structure has can be defined in linear parameters. That is, the functions themselves can be non-linear, but the combination is always a linear combination. That is, these functions are just added with linear weights. And another assumption is the models are the models that are assumed usually assumed to be good representation of the underlying physical processes or generative processes in case of non-physical data. And another major assumption is that the number of free parameters that are defined in the model are very small, and the number of free parameters is very small, is assumed to be very small. And this assumption is based on what is known as Weierstrass theorem, which says that any function, that is any well-defined function, can be represented by a combination of polynomial functions which have linear parameters. That is, the unknown parameters are linear even though the variable itself can be non-linear, but the underlying variable can be non-linear, but the parameters that actually connect all these functions are the underlying functions can be non. The coefficients of a polynomial approximation are always linear. That is a main idea of the Weierstrass theorem. For example, a sinusoid function can be easily represented by using a third-degree polynomial for a short period. For example, at least for 1 or 2 wavelengths. Second foundation is that the random component of the model, that is the distribution of a random component of the model, like we discussed previously, is always following a normal distribution. That is assumed to be following a normal distribution. And this is supported by the so-called central limit theorem, which basically says that for a very large number of random components, and which usually add up in a physical process, the final random process is definitely a random. Is definitely a normal process. This is because even though the individual processes follow different distributions, their average is most likely to follow a normal distribution. That is one of the main assumptions of the parametric approach. And the third one is the induction engine. That is the optimization tool to find the underlying functional dependency. That is for example, in the parametric approach, to determine the parameters. So maximum likelihood method is the most commonly used method. Even to this day, there are many models or many fields in which maximum likelihood method is still used for finding especially for finding unknown parameters. So theory behind this idea is that there are many mathematical proofs that say that an asymptotically optimal solution exists. If an asymptotically optimal solution exists, then it is possible to infer that function or infer those parameters basically from small set of samples or a small sample of the real world data. So these are the three main foundational ideas behind parametric approach. However, because of the advent of the modern computers and application of this computing technology for solving many real world and research problems, scientists and statisticians have found many problems with the parametric approach. The first one is famously known as curse of dimensionality, which basically says that as the number of free parameters increases, which actually in real world applications are not very small. For example, when you are trying to represent social media data or market data, you usually have hundreds of parameters influencing the observations. So in order to represent these hundreds of parameters, you need exponentially large amount of computational resources. That is, as the number of parameters increases, the required number of computational resources also increase exponentially. And the second problem is related to the polynomial, the assumption of polynomial approximation of the underlying functional dependency. That is, basically the idea is the accuracy of this polynomial approximation depends on the availability of the derivatives of the underlying function. For example, if the function is very smooth, there you can obviously assume that it can have infinite number of, very large number of higher order derivatives. But if a function is not so smooth, then it is bound to have a zero value for some certain higher derivative. It is definitely going to have a zero value. And then in this case, the linear models fail. That is, the linear model in parameters fail. Especially the polynomial approximation, the accuracy of the polynomial approximations reduces. So these two problems basically shake the first pillar, that is the functional dependency. The second one is the many real world problems are found to actually follow non-classical probability structures. And Tukey found out that the models that actually that are built to understand these observations should also take this non-classical structures, that is non-classical probability structures, into account in order to infer their functional dependency. And finally, the induction engine, that is the maximum likelihood method, is found to fail in some approaches. That is, for example, James and Stein found out that there are methods, especially in terms of approximating large number of parameters, estimating large number of parameters. There are methods that are uniformly better than the maximum likelihood estimation. Hence, a new statistical inference approach is required in place of the parametric approach. So far, we looked at the problems with classical approach, that is the classical approach for machine learning. Now let us look at the empirical risk minimization principle. Starting with some history of this ERM principle, Rosenblatt, who is actually a physiologist, worked on what are known as perceptrons. These perceptrons are basically the precursors to artificial neural networks. They have a principle. The principle is basically derived from the structure of neurons in the brain. Rosenblatt demonstrated that the perceptrons have very good generalization ability. We will learn about this generalization ability. We will learn about this concept later. In simple terms, it is the ability of a learning machine to predict the categories of unknown or unseen samples or feature vectors. So the goal of empirical risk minimization, the goal of empirical risk minimization, the ERM principle, is to minimize the number of training errors, which is basically the empirical risk, and as a result achieve good generalization ability. Now the relation between the research on perceptrons, the relation between the research in perceptrons and other learning machines which are actually similar to perceptrons in terms of their generalization ability is that they all have an underlying theme. That underlying theme is nothing but the ERM principle, that is the empirical risk minimization. They were all trying to minimize this risk function. For example, if you observe the basic classical approaches for pattern recognition, such as maximum likelihood method and also the Bayesian decision rule, we can see that these principles are actually special cases of the ERM principle. So when you actually choose an appropriate risk function. For example, if you use the mean square error as a risk function without considering the cost of making the decision, it is nothing but the maximum likelihood method. And in further research on empirical risk minimization, it was found out that it depends on what is known as the uniform law of convergence. It depends on what is known as uniform law of large numbers. Technically, this means that the necessary and sufficient conditions for the consistency of empirical risk minimization is that the uniform law of large number holds. So the research in ERM principle related to ERM principle later was concentrated on finding whether this uniform law holds in a particular problem. So the general idea behind this uniform law of large numbers is that the observed frequency of events, that is what you learn from the observations, should tend towards the true frequencies, that is the actual frequencies of these events. Of course, when you take this happens only when the number of observations increase, that is in the asymptotic case. This is basically related to the idea of uniform convergence. Now let's look at the definition of VC dimension. In the classical approach, the complexity of a learning machine or the complexity of inference is seen in terms of the free parameters, the number of free parameters that were chosen for a functional structure. So they assume that this type of description or this type of assumption describes the complexity of an inference engine or a learning machine. But later, Vapnik and other researchers claimed that the notion of complexity that is defined in terms of number of free parameters is not an appropriate approach, or it is insufficient to explain the ability or learning ability or generalization ability of a learning machine. So they introduced new concepts of capacity, that is measured by so-called VC dimension. Basically, VC dimension stands for Vapnik and Chervonenkis dimension, after the people who introduced the concept. So consider a binary classification problem in which we have n data points. So for this type of classification, we can clearly see that there are 2 power n possible ways of labeling these n data points as positive and negative examples. So for example, see, if you have 2 data points, then obviously you can name these 2 data points as class 1 and class 2, or class 0 and class 1 in 4 possible ways. That is 0, 0, 0, 1, 1, 0 and 1, 1. And now we have to understand, in order to understand VC dimension, first we have to understand we have to understand the concept that a class H shadows n. This idea is basically that if there is a hypothesis, this idea can be explained as follows. Basically, if there is an hypothesis H, small h, that belongs to the class of hypothesis capital H, that completely separates the 2 classes, that is, completely separates the positive examples from negative examples in the n of the n from the n points that we have, then we can say that H shatters n. The maximum number of points n that can be shattered by a particular hypothesis class, that is capital H, that is a class of hypothesis H, is called its VC dimension, and it is usually denoted as VC of H. Let me repeat. That is the maximum number of data points that can be shattered, that is completely classified as positive and negative samples by a particular class H that would contain multiple hypotheses small h, is called its VC dimension. Let me repeat. The VC dimension is the maximum number of points that can be shattered by a hypothesis class H. We will discuss the concept of VC dimension in details later, but for a simple example, I will say that a rectangle that it has its sides parallel to the axis of for example, if there are only 2 features, that is, if a rectangle has its sides parallel to the axis, then we can say that it can shatter only 4 points. That is, its VC dimension is 4. Now let us look at the main ideas of structural risk minimization principle. So let us recall that the learning problem, the goals of learning problem is basically to choose a learning machine that minimizes both the training errors and also should have smallest VC dimension. So, but in machine learning, it is found that these 2 goals are often contradictory. So the structural risk minimization principle actually gives a framework where we can actually achieve a compromise between these 2 requirements, that is, between the training errors, minimizing the training errors, and also choosing the hypothesis that has the lower or smallest VC dimension. So basically the idea is to choose a hypothesis that minimizes the error and also has the simplest VC dimension or smallest VC dimension. That also has smallest VC dimension. This idea of structural risk minimization principle is basically similar to Occam's razor. And in this principle, Occam's razor, this idea is often stated as modified Occam's razor, which is basically explanation that the explanations with the smallest VC dimension is always the best explanation. Whereas common Occam's razor is basically known as simplest explanation is the best. That is, when you have multiple competing hypotheses for explaining a given set of observations, you always choose the hypothesis with the simplest number, which is the simplest, that is, within the smallest number of free parameters, for example. Now let us look at the idea of inference from a small sample, that is a very small data set. Let us look at the main principle for inference from a small sample set, from a small samples data. That is, for example, in biological research or biotechnology research, it is very difficult to obtain training data. So here, small sample data sets are very common. So the goal is to basically infer the categories of test samples by learning from from training from these small data sets. So the approach is the preferred approach is to directly use the training data to make predictions about the categories of the test samples. For example, in a parametric regression problem. And a good example for this kind of application is support vector machines. And Basically, the idea is that we do not want to solve the general intermediate problem of inferring the probability density function or conditional density function of the categories or the likelihood function of the data. We want to directly use the data. We want to directly use the data to infer the categories or predict about the test samples. So the philosophy is that even the small data set may have some representative information in order to make predictions about the test samples, but it may not have sufficient information to infer the likelihood densities or posteriori densities. So that is the main idea of transductive inference. So for example, let us look at this plot. We have two classes shown in green and red, and this group is class 1 and this is class 2. These are basically not separable linearly, but they can be very well separated by using the concept of support vector machines. That is a good example of, and that is transductive inference. That is, you are directly inferring the, basically you are using the support vectors to make predictions about the test data instead of finding the probability densities of the, posterior probability densities of the categories based on data. You just use the test support vectors, that is these vectors at the margins of the classes to determine or predict the categories of the test data. So this concludes the first lecture on statistical learning theory. Thank you.